In this video, we're going to look at the standard states of formation, and heat of formation from standard states, I should say. But first we need to define what a standard state is. A standard state is basically a set of conditions, which happen to be 1 atmosphere and 25 degrees. We had standard state with pressures, but that was at 1 atmosphere and 0 degrees Celsius. But basically what it is it's a way of comparing thermodynamic data. So if somebody in Georgia does an experiment and they want to be able to talk intelligently about the results with somebody from, I don't know, China or United Kingdom or somewhere else, then it helps to be able to relate that. And so by having something defined as a standard state, you're comparing apples to apples. So that's what a standard state is. The other term that we're going to define is an allotrope, which is one or two more distinct forms of an element in the same physical state. So this is an image from the textbook, and this is sulfur. And sulfur comes in two forms. I call this the candy sulfur, and this is the needle sulfur. And basically the difference between, they're both just S, okay, and I think they're even S8. The difference between these is how the atoms line up. We talked about earlier in this chapter carbon, when we were doing problems before in Hess's law, and the fact that they specify it's graphite because carbon, of course, comes as graphite, which is what used to be used in the leaded pencils, and it also comes as form as diamond. And those are just basically two different ways of arranging the elements inside of the solid. Of course, carbon comes in a bunch of different things now that we're much more familiar with. The Mr. Fullerene molecule, and of course, what's taking over the manufacturing world is graphene, which is not graphite, but graphene, because it's very, very strong, but it's very, very lightweight. And so a lot of sporting equipment is now made with graphene instead. So a reference form is simply the stablest form under thermodynamic conditions. And so, and more importantly, the reference form, the delta H of formation, which I'm going to get to in just a second, but it's symbolized as the heat of formation, for the reference form is 0. And this is just an arbitrary amount that they have set, but it's going to be 0, it's actually kilojoules, for the reference form. So in other words, sulfur in one form from the previous page, the delta H for sulfur, and they do it by the arrangement of elements. One rhomic is 0.360 kilojoules. And the, oops, I got that wrong. Rhombic is the reference form, sorry. And delta H of formation for sulfur, and the monoclinic form, is the 0.360 kilojoules. And going back, this, what I call the candy sulfur, is the rhombic, and this is the monoclinic form over here. So this is the reference state, and this is the state in which it's not 0. So the standard enthalpies of formation, which is what I just introduced there, is the enthalpy to form 1 mole of the substance from its elements in their reference forms in their standard states. This is a table that shows you 6.2. Appendix C is like 3 or 4 pages long and has a much more list of this. You see here the monoclinic sulfur and the rhombic form of sulfur. Whoops. Also, here is, I talked about diamond, carbon for diamond, and carbon for graphite. Graphite is the reference form, and diamond is the not reference form. So the reference form is the one that's going to be 0. And so basically all of these, you'll notice, will have a 0. Bromine as a liquid is the reference form. Calcium as solid. Metal is the 0 form. Oxygen, O2. The diatomic oxygen is O2. That's a reference form. And like I said, there's Appendix C in the back of the book that has about 4 or 5 pages of this. Okay. So we're going to use standard heat of formation. It's going to be given to you to calculate the energy required to change physical states or to calculate the heat of reactions. And we introduced this earlier, the fact, and this should have a little knot there for standard state, that it's the heat of formation, or it's the heat for the products minus the heat for the reactants. The N and the M here are to multiply by coefficients. Okay, so and this just means, do a different color here. This is a scary looking symbol, but just means to sum or add. That is all that means. So you add up the delta H of the formations, you add up the delta H of the reactants, and you subtract them. So this is my final minus initial, basically. So here's a problem here. That carbon disulfide is a colorless liquid. When it's pure, it's nearly odorless, but the commercial products smell bad. And it's used in the manufacture of rayon and cellophane, which are plastics. And when you burn it, it forms this reaction. And it wants to calculate the standard enthalpy change for this reaction. So that wants to know what is delta H not equal to. Okay. Now, from the back of the book, I looked these up, and carbon disulfide is 89.7 kilojoules. Oxygen, we just saw a second ago, is 0 kilojoules. Carbon dioxide is a negative 393.5 kilojoules. And sulfur dioxide is a negative 296.8 kilojoules. And so you can actually go and find them in a table. Like I said, this is a shortened form of the table. Here's the carbon disulfide as the gas. Sulfur dioxide as the gas is minus 296. So these numbers just came from this table, basically. And the delta H then is remember, it's the sum of N times the delta H of formation of the products minus the sum of the delta H of formation of the reactants. So how do I do that? This equation is given to you, but basically, so the delta H is the products. So I have one carbon dioxide, so it's in parentheses. It's going to be the delta H of formation for CO2, plus I have 2 sulfur dioxide, so it's going to be 2 times the delta H of formation of SO2. And that's my only 2 products, so I close parentheses, minus, I have 1 carbon disulfide, so it's going to be specified 1 delta H of formation of CS2, plus I have 3 oxygens, so it's going to be 3 times the delta H of formation of O2. Okay, and now that I have this formula, I just plug in the numbers. So I have a negative 393.5 plus 2 times a negative 296.8 minus 89.70 plus 3 times 0. When I add these two up together, I get a negative 987.1 kilojoules minus, when I add this, of course 3 times 0 is 0, so this just becomes 89.70. I add these two terms together. This is a negative 1076 kilojoules, and it may ask you, it doesn't in this one, this is exothermic. And it's simply exothermic because it is negative. Okay? So, in the next video, I will do this problem here.